What's up, everyone? This is part 2 of 1.2 basic classes of functions. We'll be delving into polynomials. So let's get started. Alright, so let's go over polynomial functions. So what are polynomial functions? Polynomial functions are functions with variables and coefficients. Variables and coefficients that involve only multiplication, addition, subtraction, and non-negative exponents, non-negative integer exponents. That's a lot of words. I'll give you some examples so that you can understand this better. So let's clear my screen. Alright, so some examples include x to the fifth, 2x plus 3, as we saw before, 5x squared minus 4x plus 1, 99x to the 99th power minus 88x to the 88th power. These are all valid polynomial functions. This is also a valid polynomial function. So here we see we're not doing any dividing. It's just multiplication, addition, and subtraction of x terms or just constants that have only positive integer exponents, if that makes sense. Alright? Here are some examples that are not polynomial. X to the negative first, that's a negative exponent. Sine of x, that's not addition, subtraction, or multiplication of x terms. 1 over x, that's division. Square root of x, that's not an integer exponent. And there's just countless number of more examples I could give. But yeah, these are what polynomial functions are. So let's talk about what degrees of a polynomial are. So the degree of a polynomial is the highest power that x is raised to. Alright? So, I'm going to go give you some examples. Alright? So, question 1. 5x squared minus 2x plus 1. 2. 3x minus 1. Question 3. 7x to the 8th power plus 6x to the 7th power. And 4. 99x to the 999 plus 1. Alright? So, let's look at question 1. Question 1 is a second degree polynomial. All right. Question 2 is a first degree polynomial. Question 3 is a 8th degree polynomial. Let me write that 8 better. What is that 8? 8th degree polynomial. And question 4 is a 999th degree polynomial. None of the other x terms matter. It's all about the highest power that x is raised to. And this is just technically just 1. Alright, and one more thing I wanted to cover regarding polynomial functions are end behaviors. Alright, so even degreed, I don't know if degreed is a word, but basically polynomials with an even degree share the same end behavior. Alright? An odd degreed share opposite end behavior. Alright? I'll go show you what that looks like in the next slide. Okay, so let's go take a look at what even degreed polynomials and how odd degreed polynomials look like. So basically an even degreed polynomial, it either goes down and goes back up, so it starts at like infinity and goes back to infinity, or it starts at negative infinity, goes up, does some stuff, and in the end it goes back down to negative infinity. So they start at infinity, end at infinity, or they start at negative infinity and end at negative infinity. They start and end at like the same, with the same sign. Alright? But odd polynomial functions, they either start at like negative infinity and end at positive infinity. So they go from like the bottom left corner to top right corner. Alright? Or they go from positive infinity to negative infinity. So even they change directions, and then they go back to where they came from. So from positive infinity to positive infinity, negative infinity back to negative infinity. But odd, they don't change directions. In the long run, they just go from negative infinity to positive infinity, or from positive infinity to negative infinity. So that's what I mean. These are opposite. These are the same. Alright, so let's go discuss finding roots of functions. So what are roots? Well, roots are basically when the function equals 0. Okay, so the easiest one is if it's a linear function, alright? So if you have like 0 equals mx plus b, you just subtract b from both sides, you get minus b equals mx, you divide m from both sides, and you get x equals negative b over m. Alright? So I hope y'all know how to do that. I mean, we're taking calculus. I think being able to solve for x is good to know, to say the least. So we can also find roots of polynomial functions if they are factored to begin with. So for example, I'm going to show you an example of what I'm talking about. So factored form, all right? So here's a polynomial in its factored form. So we have 2x minus 3, 3x plus 4, 5x minus 2, and yeah, let's just have these terms, all right? So what you're going to do is you're going to set each term to 0, all right? So I'm going to have 2x minus 3 equals 0, 3x plus 4, set that to 0, and 5x minus 2 to be 0. Alright? Because the thing is, if any one of these terms are 0, then the entire function ends up becoming 0. Doesn't matter what these two terms are. If one of these are 0, then the whole function it becomes 0. Alright? So, let's see. X equals 3 halves, and x equals negative 4 thirds, and x equals 2 fifths. I should write x equals just to be extra specific. So that's how you'd find it for factored forms. Now there's one special family of functions that I'd like to discuss when we're talking about finding roots of functions, and they are the quadratic functions. Quadratic functions are second degree polynomials, alright? So they have the standard form of y equals ax squared plus bx plus c. When you want to find the roots of these quadratic functions, you would arrange the equation so that you get 0 equals ax squared plus bx plus c. And now there's a special formula that are exclusive to quadratic functions, but they work for any quadratic function. If you're not able to factor a quadratic function, you can use this special formula, alright? And it's called the quadratic formula. Haha, very creative, I know. The formula goes minus b plus or minus square root of b squared minus 4ac all divided by 2a. This is the quadratic formula. When you plug in a, b, and c into this function, you will get the solutions of the quadratic function. If b squared minus 4ac, everything inside the square root is positive. Alright, and that's one thing that you have to be careful about when you're using the quadratic formula. Because some quadratic functions don't have any real solutions. I'll show you an example. So this quadratic function, you see this quadratic function, this parabola, does not intersect the x-axis at any value of x. This does not have any real roots. On the contrary, this parabola intersects the x-axis at these two x values. So if you plug in the blue parabola's a, b, and c coefficients into the quadratic formula, you will get a negative square root in there, which means that there are no real solutions. If you plug in the pink parabola's coefficients, the pink quadratic function's coefficients into the quadratic formula, you're going to get a positive number under that square root, and the quadratic formula will spit out the correct solutions for the quadratic function. So that's a special thing, the quadratic formula.